going to look at relative velocity and acceleration today. Also related to this is another topic that we refer to often as instantaneous center of rotation or instantaneous center of zero velocity. So as by way of introduction to this topic, thought I'd just go ahead and at least present the basic idea, and then we will go ahead and do an example problem that hopefully makes it even more clear exactly how to do these types of problems. So in the first image up there, you see what I'm trying to represent is a body that has 2 points on it, A and B, and because it's a rigid body, those 2 points maintain relative to the body, they maintain their positions relative to one another within the body, but the body itself is allowed to rotate as well as translate. And so this is, we're kind of getting into here the idea of not just pure rotation, but the idea that you can have a body that both translates and rotates at the same time. And so I'm representing that here and showing that when this happens, point A kind of moves from one position to another, and then point B moves from its initial position to another position. And when it does that, the relative position vector, RB, with respect to A, doesn't change in length, but it does change in orientation as it begins to move in that way. And the book actually goes through a lot of stuff to derive the equations that I'm just going to give you. I decided I wouldn't go back through and try to rederive those, at least not for this lecture. What I want to show then is if we kind of imagine, what we're seeing here is that is a finite amount of motion, right? We can see how much it moved. But it's possible for us to scale that back to the point where that was an infinitesimally small movement, right? So imagine now that that's an infinitesimally small movement. And once we do that, we can bring it down to the second diagram and look at just the one picture there. And the lengths of those two vectors then, VA and VB, I've labeled them as VA and VB because they would be proportional to those velocities, right? You some fixed little period of time, it did that little motion, so the amount of distance it did through that period of motion divided by time, that gives you velocity, and we're using just an infinitesimally small period of time, okay? And I guess the first thing that I will show you here is just the equation for the velocity of B relative to the velocity of A, okay? And that equation goes like this. The velocity of B as a vector is equal to the velocity of A as a vector plus the angular velocity of this body, okay, and I'll show that also as a vector quantity, crossed into this R vector of B with respect to A, which is the direction that I've shown it there, right? The arrowhead going from A to B, that is the position vector of B with respect to A, or relative to A, okay? So once we get things defined in terms of vectors, we can work that out with that vector equation. And keep in mind, anytime you're using a vector equation, what you're really doing is you're containing a few equations into one way of notating it, right? And so we're going to use that fact whenever we get ready to solve for some of our unknowns, and we'll get to that whenever we get to the actual problem. But my point is there's more than one equation encapsulated into that vector equation. All right, as we look at this, basically one way of thinking about it is that you have a particular velocity of A. If you had that exact same velocity of B, you would have pure translation. And so what you see is this second part is what happens due to rotation. And that makes sense that it would be something like an angular velocity times a length that would give you another little piece that would be another kind of piece of linear velocity, so to speak, okay? So that's what the little pieces there mean with respect to the velocity. As long as you can do algebra, you can basically do that method I guess the other piece, though, that I would have to say you'd have to be able to do is to draw a good kinematic diagram. That's another piece that really makes that possible. I want to go back, though, because this other method of dealing with velocities that I mentioned is called instantaneous center of rotation or instantaneous center of zero velocity. This is actually an easier way, in my mind, to visualize what the thing actually means, okay? And so I want to show this by doing this. With instantaneous center of zero velocity, what you do is you identify, if you can identify two locations, or the velocities at two locations, right? If you can identify the direction of the velocities, then what you can do is draw lines that are perpendicular to the lines that define the direction of the velocity, like this, right? So you draw a line here, for instance, that's perpendicular to that velocity at point A, and I can draw another line that's perpendicular to the velocity of point B. All right? And as I do that, there will be some location where those two perpendicular lines cross. All right? Where those perpendicular lines cross, this is what we call the instantaneous center of rotation, or I think in the book they actually call it the instantaneous center of zero velocity. Okay? And it is very much what it sounds like. At this instant, okay, it doesn't last longer than just this moment in time, but at this moment in time, the motion of that body is exactly the same at this instant as if we had it fixed at that point that I just identified, as if we had it fixed right there and that it's moving around that point. Okay? And that instantaneous center of zero velocity, if we were to let this motion play forward in time, it would move around, right? But at this instant, we can say the motion of it is exactly the same as if it was just purely rotating around that point. And as long as we can identify those perpendicular lines to the velocities at 2 points on a body, then that allows us to find where this instantaneous center of zero velocity is. Okay, and you don't need to actually visualize the second body. I mean, the same thing could be done down here, right? You can draw a line perpendicular like this. You can draw a line perpendicular like this. And wherever those two lines intersect, that is where we have this instantaneous center of zero velocity. What this does for us is it actually allows us to do some calculations rather than getting into all this vector notation. It allows us to do some calculations with calculations that look more scalar in nature. So that's another aspect of what we're going to do in just a second. Remember that when we're doing the instantaneous center of zero velocity, you got to go back to one of the principles that we learned. If you have a body that is fixed axis rotation, kind of like this, we had relationships, for instance, between the angular velocity omega and the instantaneous linear velocity. Let's say there's a point right here. The instantaneous linear velocity is going to just be omega times r, right? Or the magnitude of the velocity there, the linear velocity is going to be just omega times r. That's basically the only relationship then that we need to know when we're doing instantaneous center of zero velocity. All right, so those are the two ways that we have in our tool belt that we can deal with the velocity question. If we know the velocity of one point based on the workings of the mechanism in which we are dealing, we can figure out what the velocity is of another point. This doesn't work the same way as for acceleration. In other words, we cannot do this instantaneous center of zero velocity method for the acceleration question. It's a different thing. We pretty much, we pretty much have to. Some people probably dispute that. There probably are geometric ways that we could deal with the other question, the question of acceleration. But to me, about the only way that I want to approach this is just with vector notation to figure out the acceleration of another point with respect to the first point. And here's the equation. So let's say we're trying to figure out what the acceleration vector is of point B. We start by identifying what the acceleration vector is of point A, and then we add, okay, a term that is the angular acceleration vector crossed into the position vector of B with respect to A. Okay, that much of it so far should make sense to you. Why is that? All right, it should make sense because it has the exact same form right now as the equation that we just looked at, right? Basically, what we're looking at there is this, you know, what we had here was this was kind of like a tangential velocity. Would you agree with that? That's kind of what that term was. Well, this is a tangential acceleration. But what we know about acceleration is that when we're dealing with it and we're not dealing with straight paths, we don't have just a tangential component of acceleration, we also have a normal component of acceleration, or sometimes we refer to that as a centripetal component of acceleration. And so we add onto this, or actually we subtract off a omega squared. This is just the scalar value of the angular velocity squared multiplied by the position vector of B with respect to A. Okay, so there's a couple things I want to say about this. First of all, we can kind of think of this as a normal or centripetal component of acceleration. Okay, because it is a centripetal component of acceleration, that is actually what explains the negative sign that we have right here. What it's doing there is that acceleration, if you're imagining, kind of imagine this, imagine what if A was being held still, because what we're trying to do is find the acceleration of B with respect to A. So if you kind of imagine for a second A being held still and there being an angular velocity around A, you would see that point B would have a normal acceleration toward point A. Would you agree with that? If it's rotating fixed about point A, point B would be having this acceleration component toward A. That's what that normal component would be, or that centripetal component would be. That's what explains the negative sign, because this vector B with respect to A is the vector pointing from A to B, right? Whereas the direction of the acceleration goes opposite that vector. Does that make sense? That's why the negative sign shows up right there. All right, so these two kind of you can think of as being tangential, and this one down here is what we can think of as being a centripetal component of acceleration. I'll change the color a little bit, kind of give us the idea that that's what these points or these terms in the equations mean. All right, that's about as much background as I want to do. What we want to do now is move on and see how this applies to an actual mechanism. All right, so here's the example problem that we're going to do. Okay, so we have this wheel centered at A, and there's a point at B also on that wheel. That point at B is described by a radius of 7 inches relative to A and an angle of 80 degrees. Okay, and that's at this instant in time. The thing is in motion though, so all of our analysis that we're going to do right now is basically taking a snapshot and thinking about this instant in time. All right. We are also given here the position of point C relative to point A. Okay, notice, and that's again, that this instant in time, we're given the position of point C relative to point A. And we're given that with the 12 centimeter and 24 centimeter dimensions that are listed right there. All right. We're also given that in the direction shown for the little green arrow, point C has a rightward velocity of 16 centimeters per second, but it also evidently is slowing down, okay, because it has a negative acceleration of 29 centimeters per second squared. Okay, so it has a rightward velocity at this instant in time, but it has the tendency that it is slowing down, i.e. a leftward acceleration. All right, quick thing I'll note too before I get into what we're supposed to find. I've already given you what x and y are for this, so that's what I'm going to use for my x and y directions. What we're supposed to find is this: the velocity of point B and the angular velocity of member BC using relative motion analysis. That is that vector equation that I gave you just a second ago. What we're going to do after that is do it a second way. We're going to find the velocity of point B instead using the instantaneous center method. Okay. After that, we're going to use our relative acceleration analysis to figure out the acceleration of point B. And then from there, we are going to go on and figure out what the angular acceleration is for the wheel, the thing that's centered at point A. All right, so we'll start with part A. The velocity of point B and the angular velocity of BC using relative motion analysis. So here's our basic equation. Okay, basic equation is that the velocity of point B is equal to the velocity of point C, all right, plus the angular velocity of member BC. And I'm going to put a little subscript on here to make sure that we understand we're talking about link BC, okay, because there's actually two bodies in this problem that are rotating, correct? We have link BC that has some rotation happening. We also have wheel AB that's rotating, okay? And it's going to be that vector crossed with the r vector of B with respect to C. All right? And the reason we know this is the equation we want to use is that we already know the velocity vector of point C. That's a piece of given information that we have. So we need an equation like this to figure out what the velocity is of point B relative to that point C. Okay? What I want to do at this point is actually draw member BC, because this is a really key sort of step of the process, is make sure that we can visualize the different pieces that we're talking about. So let's say that that's point B, and down here we have point C. Okay. All right, so the first thing I'll say is that we know the velocity of point C, right? We know it because point C has to slide against that surface down underneath it. So that surface down underneath is constraining the motion of point C to be purely horizontal. That means that we know that there cannot be a velocity component and there cannot be an acceleration component in the upward direction, the up and down direction for point C. Its velocity and acceleration have got to be horizontal along that surface. Okay? And so I'll say I know that value is 16 centimeters per second. Okay? So maybe say V sub C, the entire V sub C is just the x component of V sub C, and it is going to be 16 centimeters per second. All right, so far so good. That's kind of the easy part. All right, the next one I want to look at is point B. Okay. Do I know anything about the velocity of point B? Well, I'll say this. I don't know much about it, but I don't know zero about it either, right? I do know something about it. Here's what I know about it. I know that point A is over here somewhere. Okay, I'm going to draw it like right here. This is point A. And I know that body AB has to rotate around point A. Okay? And because body AB is rotating around point A, that means that I know, I'll kind of use this term, I know the instantaneous center of that rotation because it is a fixed axis rotation around A. All right? So that means that I can say with certainty the direction of the velocity of point B. I'm going to stick that up there real quick. And it's going to be perpendicular to that line that goes from A to B. Okay? So that's a perpendicular relationship right there. All right? I don't know, as I start off the problem, I don't know what the magnitude is of this. This is one of the things I'm trying to find. So I'll just name the magnitude of that vector, I'll name VB, like this. Okay? Now here's one of the things that's interesting. That means, since I know the direction based on the geometry of this thing, since I know the direction of that velocity, if I want, I can split it into components. Right? I can split it into a component that is vertical, and I can split it into a component that is horizontal. Would you agree with that? Okay. And that vertical component that I have over there, I can find it because I know this angle. Okay, I'll go ahead and show this here, like this and like this. These are my x and y directions. I know this angle right here is what? At this instant in time. That angle should be 80 degrees. Okay? And these two components that I just identified right here, this one is going to be VB times, all right, the cosine of 80 degrees. And this one down here is going to be VB times the sine of 80 degrees. Okay? And the reason I'm kind of beating this home, or kind of driving it home, is that I'm trying to make the point that I only have one unknown as far as the action of point B right there. I only need to know the magnitude of it. I already know the direction, which means that my two components that I have there, I can define both of them in terms of just one thing that I don't know. All right, so now that I've got my little diagram set up, let me go ahead and start identifying all these vectors that I have in this equation, VB, VC, and then omega BC and R of B with respect to C. So VB. Okay. If I'm going to state this as a vector, what I would say is that VB is equal to just the magnitude of VB times the cosine of 80 degrees. Okay. And then that is going to be multiplied by I. Okay. Then I can add to this, and actually it turns out to be subtracting because it looks like it points downward here. I subtract off VB times the sine of 80 degrees times J. Okay? So now I've expressed VB as an actual more formal vector where I just have one unknown. Next, I want to express VC. Okay? So VC is actually pretty easy. It is just going to be 16 centimeter per second I. Okay? Notice there that its velocity is entirely horizontal, right? And it goes to the right, which means it's positive. Okay? So far, so good there. Next, omega BC. Okay, this one is just a smidge tricky, but it's not that bad. Omega BC is not something that we know yet. Okay? We don't actually know what the magnitude is of omega BC. But let's just say here that we express its magnitude as just omega BC. How do I think of that as a vector? Okay? And this being a 2D problem like this, 2D problems in X and Y like this, all the rotations that you have to be around the Z-axis. It's pointing out at you, right? So my omega BC is just going to be equal to omega BC times that unit vector in the Z direction coming out at you, okay? All right, so there's my omega BC. Now what is R of B with respect to C, or B relative to C? Okay, R of B with respect to C is just going to have to be handled with a little bit of geometry. Okay, so here's how I would kind of approach that. I would say that I happen to know the length from point C to point A. That's 24 centimeters. Okay, and again, this is just right now at this instant. What I want to know, though, is how far do I have to go from C to B instead of from C to A? All right, that's what I want to know is what's this length. Okay, so I have to subtract off what? Well, I have to subtract off a little horizontal length that I can find given the fact that I know the radius from A to B. Right, that was one of my given pieces of information, was that this is 7 centimeters. Okay, what that tells me is that this little amount over here is 7 centimeters minus, excuse me, not 7, this is 7 centimeters times, okay, got to think about the trig there. It looks like what that should be is 7 centimeters times the cosine of 80 degrees. Cosine or sine? Let me ask that. I want to make sure I don't screw this up. Okay, because I may have misspoken. Okay, let's think about that. So this is 80 degrees. Am I trying to find the adjacent component or the opposite component relative to where that angle is being measured? Okay. The adjacent component is basically going to be finding the height of that length from A to B. That's not what I want. I want the horizontal length. Okay. So I think I misspoke. I want the sine function, not the cosine function, to get that horizontal piece. Okay, so this is 7 centimeters times the sine of 80 degrees. Okay, which tells me that what I have over here is 24 centimeters minus 7 centimeters sine of 80 degrees. Let me just go ahead and calculate that real quick. 24 minus 7 times the sine of 80 degrees. Okay, that tells me that what I have left there is 17.12, we'll say. Okay, and because I might actually want that stored in my calculator, let me go ahead and store that into, let me just store that into A. All right, so that's one of the pieces that I wanted to know. And when I define my R vector down here, do I want to make that value positive or negative, do you think? 17.12 centimeters I. Okay. When I have B with respect to C, or B relative to C, what direction am I defining that vector? Where do I put the head of the vector versus the tail? Right? It goes like this. Whenever you have B slash C, the head goes at the first one, right? So there's going to be like the head of that R vector up here, and the tail is back there, which means that when I define this vector, I need to define it with a negative because I'm going to the left where X is positive to the right. Does that make sense? Okay, so there's that piece. What's our other piece? Looks like I might have to kind of work on it over here. Our other piece happens where I know the height from point C up to point A. That's going to be 12 centimeters. But then I have a little bit more that I need in order to get up to there. So what's that height? Well, now that we've done the other one, it's probably fairly obvious to see that this one should be 7 centimeters times the cosine of 80 degrees. Okay, and so the total amount of height that I have here to here is going to be equal to 12 centimeters plus 7 centimeters cosine of 80 degrees. Okay, and that just gives me 13.216, we'll say. You can see these diagrams get pretty messy pretty quick. All right, positive or negative? Do I have to go up or down to get from C to B? Because up is my positive y direction, right? So it looks like I have to go up to go from C to B, which that tells me this should be positive 13.216 centimeters. J. All right, now we have defined all of the pieces that we need for our vector equation. There's one piece that before I start writing my vector equation, there's one thing I want to do real quick, and it actually applies for a lot of these cases. It basically applies to 2D cases, which is going to be a lot of what we do is 2D kind of things. If you think about how this cross product, where you're going to have a angular velocity around a z-axis and then a vector that's basically in the ij. Does that make sense? If you have a 2D case, that's what you're always going to have for your omega and your r. Let's just really quickly, sort of once and for all, kind of figure that up. So if we do that cross product, then the way we do that, or one way to do that, is to basically think of a determinant made up like this, where you have, and for our particular case, we're going to have 0 angular velocities in the I and j, and then we're going to have an angular velocity that's entirely in the k. So kind of to the side of this, just to make sure we don't misunderstand, this is for 2D motion. Okay. And then our r vector is always going to have components that are in the I and j. So let me just call those like rx and ry, and we'll have a 0 here. And if we take the determinant of this, the way that we can do that is we can copy our first two columns. Like this. And we can think about multiplying across diagonals, right? So we multiply across here, and there, and add all those yellow products, the product of the first yellow line plus the second yellow line plus the third yellow line, and then subtract the product of that green line, and subtract the product of that green line, and then the product of that green line. That's kind of the easiest way for me to remember how to do a cross product. Okay? Well, when you look at this, all of those things turn out to be 0 with the exception of 2 of them. So we would have this guy right here that would be negative, and we would have this one right here that would be positive. Okay? And so what we find here is that for 2D stuff, if you're going to take an omega crossed with r, and this is kind of with if you're dealing with your standard, you know, x and y planar motion where z is the one that's out of the plane, then what you're going to see there is that you will have minus omega ry I plus omega rx j. Okay? And this is just a little sidebar that I'm putting over here to the side so that we can more easily express what that cross product actually is when we get ready to solve this. All right. So, all that being done, we are ready to look at the 2 different directions that are implied by this vector equation. Okay? So the first direction is going to be the x direction. So I'll just put that with a label up here in the x direction. Okay? VB, what is my x component of VB? All right, it's just going to be VB times the cosine of 80 degrees. All right, that's going to be equal to, what is my x component of VC? Just 16 centimeters per second, right? Okay, and now, how do I figure out what my x component is of omega BC crossed into RB with respect to C? Okay, well, I look over here and I say, all I need is just minus omega times RY. Right? So I go minus omega. I don't know omega yet. Okay, but it's just going to be this omega BC times RY, and RY is going to be positive 13.216 centimeters. Okay. What about the y direction? In the y direction, I have a negative VB times the sine of 80 degrees, okay, is equal to, all right, my next term is VC. I want just the y component of VC. Do I have a y component of VC? I don't, right? Because VC, the velocity of C is entirely in the x. So I have 0 for that, so I just won't put anything in. And then I want the y component of omega crossed with r. So the y component is going to be positive omega. The omega there is, again, something I don't know, times Rx. And Rx is going to be negative 17.12 centimeters. All right? So that gives us a system of 2 equations and 2 unknowns. Okay, we can solve that in our calculator. Okay, well, let's go ahead and remember this as well, though. I believe we have those numbers stored into A and B. Okay, this 17.12, that's actually stored in A. And I believe we had this other one stored in B, or if we don't, then we probably can make that happen. Okay, let's check the other one. Okay, notice it's not negative there, so if we try to use that variable, let's make sure we get the sign correct outside of that. All right, so solving it in the Casio then. We'll go into mode 5. We're going to do a 2 by 2, and remember that we want to set it up so that our variables are on the left side. I'll just do that mentally as we go. So what we have there is cosine of 80 degrees. Okay. For this other one, I have, when I move it to the left side, that negative omega BC times 13.216 becomes positive. So I put in just 13.216, which is something that I have stored in B. All right. And then for my last term, it stays on the right side of the equation, so I just put in 16. All right, so that's it for my first equation. My second equation, I'll do negative sine of 80 degrees. All right, here, let's make sure we got maybe a double negation we got to handle here. This becomes positive 17.12 when I move it to the other side of the expression, correct? Remember, that is the value that I have stored in A, so I don't need to negate it because I, kind of double negates there. So we put that in, and then we have no constant term in that second equation, so we put a 0 in, and we solve, and we find out that x, which represents v sub b, is 17.122. Okay, and that would be in units of centimeters per second. An interesting second value that comes out of this is the angular velocity of member BC. So this is 0.9857. Units on that are going to be radians per second. Okay, so let me label this as omega BC. All right, and depending on what form you're looking for as far as the outcome, it is possible that what you want is, instead of just a magnitude of that velocity point B, you might want to know what are the components of it. So for instance, I might want to know what is that velocity vector. Well, it's just going to be equal to 17.122 centimeters per second multiplied by, kind of remember up here, how we defined that thing in the first place up here, VB cosine of 80 degrees, right, would be the x component. So we multiply here by the cosine of 80 degrees. And this would be my I component. And then I would subtract 17.122 centimeter per second times the sine of 80 degrees, and that would be my J component. Okay, and if I punch those in, this basically tells me that V sub B is going to be equal to 2.973 I minus 16.862 J. And this would be in units of centimeters per second. Okay, and if I wanted to figure out what my angular velocity is in terms of my vector, that one's even easier because all I got to say is this. It's just omega BC is going to be equal to 0.9857 radians per second. I'll go ahead and put that in, radians per second. Okay. And physically, what does that represent as far as the direction that the link BC is tending to rotate? Counterclockwise or clockwise? Okay. So what that represents is, if this is a right-handed coordinate system, which you can presume that it is, you wrap your fingers from X to Y, and your thumb points in the Z, right? So that means that would be the positive Z direction, is pointing out at us, not pointing into the page, pointing out of the page toward you. So what that means is a rotation counterclockwise is represented by a positive K. Something that's positive with that K notation is a counterclockwise rotation in an XY plane. Okay, so physically that's how you interpret this positive value. Is that the angular velocity of link BC is going to be counterclockwise. Physically, does that make sense? What do you say? Does that seem to make sense? I would say it does, because point C is going straight horizontally and point B has this downward component. So if that's happening, then that little piece has got to be swinging such that it's got a counterclockwise tendency of rotation. All right, so I feel pretty good about those results. Now that was not that painful, but it was a little bit painful to have to go through all of that algebra. Wouldn't it be nice if we had a little bit cleaner method of doing this that didn't require quite all of this work? Wouldn't that be nice? All right, well, good news is there is such a thing. So I'm going to go back up here, and let me just slide all of this down. And we are going to do this same problem, but now with instantaneous centers of rotation. Okay, so this is definitely a more graphical technique of handling the same type of thing. So I'm going to show that link again that goes from C to B. Okay. Now, we know that the direction of the velocity of point C is horizontal. So we go ahead and put that on there. And we can even additionally say that we know its value is going to be 16 centimeters per second. Now what we do with instantaneous center of rotation is we draw a line that's perpendicular to that line. Okay, we can extend it as far in both directions as we want. All right. Then we look at the velocity of point B, and we remember that this also had some geometry that we were familiar with, right? From A to B, we knew that this was defining the direction that B was going. All right, that was something we called, and we're pretending at this point that we haven't solved part A yet, right? We're starting from scratch. Pretend like we hadn't done that and we don't know this value yet, so we'll just call that VB. So again, we know the direction of the velocity at point B, we just don't know the magnitude. All right, well, what is that perpendicular line to VB? You can do it just by continuing to extend this line out even further. And what we find there is that this point right here is the instantaneous center of zero velocity, which we will often annotate that with IC. Okay? Here's what's awesome. Once you find the instantaneous center of zero velocity, as far as your velocities are concerned, you can imagine the motion of this link as being a pure rotation around that point. Okay? So that means if we do a little bit of geometry, we can figure out things like an angular velocity, for instance. How would we do that? Well, if we know the length from the instantaneous center to point C, then I can take my velocity of 16 centimeters per second and divide by that length, and what I come up with is the angular velocity around the instantaneous center. So I need that length that I just drew on there, that blue line. Here's how I propose we get it. Okay? We actually know a couple of things already, right? We won't go back over the details of how to find them, but remember, we already know a couple of these lengths. Okay? I know that it is, I believe it was 13.216 centimeters up to that line right there. Okay, and it was 17.12 centimeters that went right here. Okay, so how do I come up with this additional little height right here? All right, well, here's what I would say. I also know this angle right here is 80 degrees at this instant in time. All right, and so if I think about that is also the same 80 degrees as I have right here. So what that allows me to do is to think about a tangent function. All right, the tangent function of 80 degrees is equal to the opposite over the adjacent. And so let me just call this little, I'll call this little piece right here h, just to have a variable that I can give it. All right, this tangent function is going to be equal to the opposite, which is 17.12 centimeters, divided by h, which tells me that h is just equal to 17.12 centimeters divided by the tangent of 80 degrees. Okay, So if I go back into my computation mode here, I can just take what I have stored in A and divide it by the tangent of 80 degrees. And that tells me this little h value is going to be 3.016. Okay, let me store that into C. All right. Well, now I know the length of that blue line that I drew on there, right? And so if I want to know my my angular velocity, okay, all this, by the way, we're working with part B. If I want to know my angular velocity around the instantaneous center, which it isn't necessary for me to specify that. Angular velocity is angular velocity. You don't have to say it's around a particular point. But it makes it easier to find sometimes if you know what the center of rotation is. So my angular velocity is just going to be equal to my linear velocity of 16 centimeters per second divided by that length, which is just going to be 3.016 centimeters plus 13.216 centimeters. Okay, this is the velocity, the angular velocity of link BC. All right, so 16 divided by the quantity of B plus C, which gives me 0.9857 radians per second, which should reassure us a little bit, okay? Because that's the exact same number we got whenever we worked it using kind of that relative motion analysis, the vector method. All right, well, that's all fine and good, but one of the things it's asking us for there is the velocity of point B using instantaneous center analysis. This isn't, the omega isn't actually what it was asking for, right? It wants to know what is the linear velocity of point B. Well, here's the good news about that. Once I know my angular velocity, all I got to do is now find the length of another vector that points from the instantaneous center of rotation, instantaneous center of zero velocity, out to point B. All right, so what's that length? All right, well, probably the easiest way to get that length is with the Pythagorean theorem, right? So that this length right here is just going to be equal to the square root of 3.016 centimeters squared plus 17.12 centimeters squared. Okay, so if I punch that in, okay, I believe I had that in C, and I had the 17.12 in A. So that gives me 17.37 centimeters. In case I need it later, I'll go ahead and store that into D. But what I want to do with it is just multiply now my omega BC times that length. Okay, so omega BC, we'll say the V of B is equal to omega BC times that length of 17.37 centimeters. Okay, so that gives me 0.9857 times what I had in D, and that gives me 17.122. Units on that would be centimeters per second. Okay. Interesting that we have two completely different ways of approaching it, one mostly with vectors and one here mostly with geometry, and they give us the exact same results. It generally makes us feel confident that we're probably doing it right. All right, so that's kind of the A and B parts of this. How do we handle C? We're supposed to find the angular velocity of the wheel. Okay. Well, if we actually look at the wheel and kind of draw a little diagram of it, what we can say there is that we have this point out here, point B, and now we know the linear velocity of point B instantaneously right now. Right? And that linear velocity is 17.122 centimeters per second. Okay. We also know what this radius is relative to point A. Right? This right here is 7 centimeters. Okay. And so if I want to figure out the angular velocity of the wheel, then all I got to do is take my 17.122 centimeter per second and divide it by 7 centimeters. Which gives me 2.4459, say 2.446. Okay, radians per second. Now, what if I want to express this as a vector? Okay, first of all, what axis is it rotating around? Okay, directionally, the axis it rotates around is going to be the z-axis, right? So this is going to be in the k as far as the unit vector that we multiply it by. But do I do positive or negative? All right. Is it rotating clockwise or counterclockwise, the wheel? Okay, think about if that point right there is moving down and to the right, which it is, right? Point B is moving down and to the right. It means that this wheel must be going this way. In order for that point to go down and to the right, it means the wheel must be rotating in a clockwise orientation or direction. And so that means that we would actually say that this vector would be minus 2.446 radians per second k. And that's actually a super important number that we're going to need a couple of times here in just a moment. Actually, both, that number is important, and the omega BC is also important. So let me get that thing stored. We'll call that E. All right. So those are all my velocities. That's kind of the easy part. All right. So we've come up with what the velocity of B has to be and how that translates into the angular velocity of wheel AB. Next, what we want to do is figure out what the acceleration is of point B. And this is just a little bit trickier, and this is the kind of thing that I wouldn't want to try to do this without using vectors. All right, so for part D, the first thing that I want to do is go ahead and just write out the expression that we had a second ago. So the acceleration of point B is equal to the acceleration of point C plus my alpha vector. In this case, because we're looking at the link, I need the alpha of link BC. Okay, and I'll put that little notation on there. I'm going to show that as a vector here. I'm going to have that crossed into my R vector of B relative to C. All right, but then I have to subtract off my omega of BC squared, not crossed into, but just multiplied by my R vector of B relative to C. So this is the expression that we need to work with. All right. So I guess maybe the easy things first. What is R of B with respect to C, or relative to C? We already did that one, right? So we don't have to do it again. That one has not changed. So we'll go ahead and copy that and bring it up here. Good deal. All right. What about the acceleration vector A sub C? I'm going to try to list all these vectors right here real quick. So acceleration vector C, for point C, it is entirely horizontal, right? It's not allowed to move up and down. It entirely moves in the horizontal direction. And so we know what its value is as well. It's given right up here, negative 29 centimeter per second squared. Okay. And since it's entirely in the horizontal direction, I use my unit vector I. Okay. So far, so good. Now, AB. Here's one of the things that's tricky here. AB is going to be an acceleration defined by an acceleration in an x direction. Okay, so acceleration of B in the x direction, I, plus the acceleration of B in the y direction, J. And unfortunately, with this, the acceleration analysis, we cannot assume that the acceleration is going to be along the line that defines the path of B, kind of like that tangent line, right? If you imagine a tangent line defining the instantaneous velocity of C, that much is easy. The problem is I don't have I don't have a relationship that gets established between the two components of acceleration just because I happen to know where that point is. So at this point, that's as good as I can do. I have two components that I will have for my acceleration at B until I, maybe work on that a little bit more. So I'll leave that alone for just a second. What else? Okay. Alpha BC. Is there anything I can do with that? All right. Maybe. Okay. One thing I can say is that my alpha, my angular acceleration for link BC, does have to be around an axis parallel with a z, right? It does, the axis around which it's rotating has to be in the z. And so one thing I can do is just, instead of showing it as a vector, I can just show it as a scalar and say that it is around the z-axis by showing a little k unit vector there. All right, so far so good there. And I think that actually covers everything, because what is omega BC? I guess I'll go ahead and put that in here more explicitly. Omega BC is, we calculated that in our previous step, 0.9857 radians per second. And I don't remember storing that into a variable, so let's take a moment and just do that real quick. I'll redo this calculation we had down here. 16 divided by, I believe I had the 3.16 was in C, plus, I believe the other one I had was in B. Oops. Okay, and now I'm going to store that. Let's see, I haven't used F yet, so I'll store that in F. Just to remind myself, I'll put that there. All right, let's take stock real quick. How many things don't I know? So I'm basically working with that equation up there, that vector equation. That is a vector equation in 2 dimensions. So that means I've actually got 2 equations sort of hidden inside of that one vector equation. That means I can solve for 2 things. How many things do I currently have up here to solve for? Currently I have 3, right? So since I've got 3 things that I need to solve for, and I only have 2 equations, that means I got to do something else. All right? So here's what I propose. Let's look at the wheel. So if you look at that wheel, and I'll even draw it over here real quick. Actually, I think I have it. Yeah, it's right here. I know that this angular velocity for the wheel is 2.446 radians per second. All right. That means that I can, I'm going to change my color here, orange will be my accelerations. That means that point B over here, I know what its centripetal acceleration is. All right, what is this centripetal acceleration? Instantaneously, right here at this time. Okay, that centripetal acceleration is just going to be equal to omega squared, so omega wheel squared times r, which is 7 centimeters. All right. I will also have a tangential component of acceleration. That tangential component of acceleration is going to be alpha of the wheel. Okay. Now I'm going to be very formal here and say it's really going to be negative alpha of the wheel times 7 centimeters. Okay. The reason I say that, is that if it's the direction that I'm showing there, then alpha would actually have to be counterclockwise. So what I would have is negative alpha of that wheel multiplied by 7 centimeters. And that's what that other component is going to be right there at B. Okay? Well, now what I need to do is look at those two components of acceleration and resolve them into I and J, right? Because now I can express them in terms of alpha wheel, right? And remember, omega wheel is something I already know. That's a known value. So I can now express these, both ABX and ABY. I can express all of that in terms of just one unknown, which is the alpha of the wheel, right? So I'll kind of take a little sidebar over here and do that. ABX, all right, is going to be minus omega squared of the wheel, right? So minus 2.446 radians per second squared times 7 centimeters. And then we need to add to that the contribution of the tangential component, which is going to be equal to a positive, but then it'll be a negative, right? So it ends up being a negative alpha wheel times 7 centimeters, right? Positive because the arrow points to the right, negative because I'm defining it relative to a counterclockwise positive alpha, right? Does that make sense? So basically what I'm saying there is this is the direction I'm assuming alpha is. All right. And I think those are the only two pieces that I have for ABX, right? So, I guess I'll just leave it alone at that. Next, I've got ABY. Okay. First, I've got my normal component. Oh, y'all didn't stop me. I totally missed a big part of what I needed to do. Those are the values themselves. I need to resolve them into X and Y, right? So I almost made a huge mistake right there. What do I need to multiply these by? Okay, so for the first one right here, this is my 80 degrees. Okay, would you agree with that? And so my y component would be, to get that, I would multiply by cosine of 80 degrees for that normal component. And for the x direction, I would multiply by the sine. Okay, so that means I need to take this up here and multiply by the sine of 80 degrees for that normal component. Okay, and what about for my other component that I have here? Probably multiply this by the cosine of 80 degrees. All right, now the y direction. Okay. The y direction for the normal component, it's going to be pointing in the negative direction again, as the arrow generally points downward. We'll have 2.446 radians per second. That'll be squared multiplied by 7 centimeters. And because I want to pick off just the vertical component, I multiply this by the cosine of 80 degrees. Okay. Then I look at my tangential component. It'll be pointing down, but it has a negative value right here, so I'll say plus alpha wheel times 7 centimeters. All right, times, and I just want the vertical component, so I multiply by the sine of 80 degrees. All right, here's the takeaway. What I've now done is expressed ABX and ABY where I only have one thing I don't know for those two variables. And so now I've reduced my system of equations that I should have had up there down to, if I do those substitutions, it reduces it down to just two things that I don't know in this whole equation. And so here's how I write those equations. So we'll start in the x direction. Okay. AB, right, is what I start with. That means I need ABX, and ABX can be written over here. I'm actually going to start with the negative alpha wheel times 7 centimeters times the cosine of 80 degrees. Okay, then I will put on my negative 2.446 radians per second squared times 7 centimeters times the sine of 80 degrees. All right, all of that I just wrote is the x component. It's ABX, basically, is the only thing that I've written so far. What I'm going to do now is set that equal to, because it's set equal to the x component of AC first, so this is going to get set equal to negative 29 centimeter per second squared. Okay, that's that next term. Now I need to take this cross product between alpha BC and R of B relative to C. So we'll go back and remember what we just came up with a second ago. The same thing that we did down here where we did this cross product, the same thing applies if you're dealing with alpha. So alpha cross R, if you're in 2D, ends up being negative alpha RY I plus alpha RX J. Okay, because you see there, the only thing that would change is that you'd replace omega with alpha, and so the same exact result would come out. So I'm going to copy that and let it guide us up here. Never can tell where it's going to put this thing when I paste it. All right. So for us, if we're just dealing right now in the x direction, then what I do is I take minus alpha, all right, BC, times RY. RY is just going to be 13.216 centimeters. Okay. And that is that second term up there of alpha BC crossed with RBC if I'm just doing the x direction. So then the next thing I got to do is subtract omega BC. And omega BC was way down here of 0.9857 radians per second. That's going to be squared, and we're going to then multiply it by just the x component of RBC, which is going to be negative 17.12 centimeters. So far, so good? The next one is not actually much different. It's just the y direction instead of the x direction. Okay, so in the y direction, we'll again take just the y component, the ABY right there. So that's going to be alpha wheel times 7 centimeters times the sine of 80 degrees. Okay, minus 2.446 radians per second squared times 7 centimeters times the cosine of 80 degrees. All right, again, that's all that I've written up there is just ABY, which covers that very first term of this whole equation. All right, so then the next one I got to do is AC. Well, now we get a little break because there is no J component, there's no Y component for that velocity of, or excuse me, the acceleration of C. All right, so then I need to take just the Y component for my alpha BC crossed into R of B with respect to C. And that is given over here with a positive alpha times R sub X. All right, so I have, I won't put the plus there, but I'll just say alpha BC times Rx is negative 17.12 centimeters. Okay, that comes from my alpha cross R. All right, and so then the last piece is we're going to have minus omega BC, which again is 0.9857 radians per second squared times, all right, now I just want the y component of my R of B relative to C. Okay, so that just gives me 13.216. And what we have now is a system of two equations in two unknowns. Which we can solve and get my angular acceleration of the wheel and my angular acceleration of link BC. All right. So we'll do that. Let me remind myself, there's a couple of values that I need. So my 2.446, I believe I had that stored in E. I think that's probably the only one I need to refresh my memory on. All right, so mode 5, we get to the solver for a 2x2. My first variable is going to be alpha wheel, and I'll see that my first coefficient that I'm dealing with there is going to be -7 times the cosine of 80. Okay. The next term there is just going to be a constant term that ends up on the right side of the expression. So I'll deal with those in just a minute. Okay. The next term actually that I have that is a variable term is going to be this negative alpha BC times 13.216. When I move that to the left side of the expression, that becomes a positive 13.216. And I believe I had 13.216 stored in one of my variables. Sometimes it runs together. 13.216, I believe I actually had that stored into B. We'll try that and see if that seems to make sense. All right. That's it. All right. So that's it for that side. Now I need to put a -29 as far as one of my constant terms over here. I also need a positive 0.9857, which I had stored in F. That's going to be squared. Okay, times 17.12, which I had stored in A. Okay, so that's my next term. And then my final term for my constant is going to be this, it was a negative on the left side. That means I need to turn it into a positive. So I add 2.446. Again, that one was stored into E. Squared times 7 times the sine of 80. And I think this 2, I think that was a, something got stuck up here that shouldn't have gotten stuck up here. All right. All my entries are now made for my first equation. Next equation, I'll have 7 times the sine of 80 degrees. Okay. I'll have to skip ahead here to my alpha BC. All right, which needs to move to the left side of the equation. And when it does that, the negative becomes a positive, and so I end up putting in just 17.12 in that one. Okay. Now, on the right side of the equation, I already had a negative 0.9857, which I have stored in F. Oh, and that's going to be squared times 13.216 centimeters. Okay. But now I need to add in this term that I had originally on the left side. When I move it to the right side, it becomes positive. So I add to that, I believe that was stored in E squared times 7 times cosine of 80. All right. When I hit equals, we'll have the moment of truth. Okay? So what comes out of here, the first variable, remember, that we were solving for is alpha wheel. So that gives me a negative 5.07 all right. 5.07 what? All right, it should be centimeter per second squared. And what's my other one? Alpha BC is the other variable that comes out of this, and it's going to be 1.718. Okay? And that would be, not centimeter, radians, excuse me. Radians per second squared. This one's going to be radians per second squared. Okay? What does the negative sign mean? Any thoughts? Okay. Generally, when we do these things, we assume a direction, then we solve, and we come up with an answer. The answer has a sign to it. The sign tells us whether or not the direction we assumed was correct. Okay? So the direction we assumed whenever we started all of this was that alpha wheel went that direction. The negative sign means the acceleration of the wheel is actually clockwise, not counterclockwise. Okay? When we did alpha BC, right, we came up with a positive number. What did we assume whenever we started? Well, we assumed counterclockwise. We did that step right here, basically, right? We said by showing that as a positive number right there, we assumed a counterclockwise acceleration. We were right about that one. So that one is accelerating, in a counterclockwise direction. Okay? But we haven't quite finished yet, because what we did get, actually, without even trying, we just solved E. Right? And we got the angular acceleration of the link, too, which we didn't even ask for, but now we have it. Kind of just sort of lagniappe, right? So what we need to do probably is look at the acceleration there of point B and actually interpret that as components of acceleration of point B. Okay? What's the easiest way of doing that? Well, in my opinion, the easiest way of doing that is to go back and remember that we already did that. All right? That is the acceleration of point B. Which means that all of this stuff that we did over here applies. And all I got to do is go back in and plug the value that we now know that we didn't know to begin with, plug that in, and we can get our components in the x and y for our acceleration of point B. All right? So, ABX. I'll tell you what, I'm actually going to slide this down right here so that we can see all that stuff. All right, ABX is given with this expression up here. I'm solving for AB, and so I have minus 2.446 radian per second squared times 7 centimeters times a sine of 80 degrees minus alpha wheel, and alpha wheel is now negative 5.07 radians per second squared. Okay. times 7 centimeters times the cosine of 80 degrees I. Right? And then down here, we're going to have plus, here we'll have a minus 2.446 radian per second squared times 7 centimeters. Oops, that's cosine of 80 degrees plus a minus 5.07 radian per second squared times 7 centimeters times the sine of 80 degrees, J. All right. We can punch those in. All right. Let's see, mode 1. So here I've got minus E squared times 7 times the sine of 80. Minus a minus, so I'll use a plus. 5.07 times 7 times the cosine of 80, which gives me negative 35.08. Okay, this is going to be in centimeters per second squared, and that's my I component. Okay, for the next one, I will have minus E squared times 7 times the cosine of 80 minus 5.07 times 7 times the sine of 80. Just like that. So negative 42.22. And now we've got, I believe, everything that we requested. Fun stuff? Like it or not, there it is. So we don't get to make it up, do we? We got to stick with how it really works, even if it's a pain. All right, any questions? Excellent.